So you moved certain degrees of freedom to move from the Hamiltonian to the effective Hamiltonian. So we probe the lower system. Can we use the same method to probe the upper system? So we can remove the lower degrees of freedom and keep the higher degrees of freedom.
Yes, thank you very much. This is a very important question. Actually, what I showed you, this perturbation theory is kind of difficult and not so easy to do. There is a more systematic way how one can do this transformation. It is using canonical transformations. It is like in the quantum electrodynamics, it was called the Foldy-Whitehouse, but applied to the solid state physics is the Harris-Lange or McDonald or whatever. So there is a systematic way how, if you have a Hamiltonian that has like a U, that is the largest term, there's a hopping, and then there are other terms that you expect. One can apply a canonical transformation that will remove the hopping part, and as a result, T square over U like Hamiltonian terms will appear. And they will be precisely those terms that we derive using the second order perturbation and additional ones, and they will tell how the high energy, like the splitting between the splitting that you saw, there was a double, the U energy and the small splitting T square over U there, it will be able to also describe that part. In addition, if we apply the canonical transformation to the operators as well, we will get corrections to the operators that will also describe these additional degrees, this higher, the effect of higher bands. For example, if you apply to a density operator in this picture is very simple, but if we apply it to this canonical transformation to the density operators will get a part which will describe this this higher higher energy states as well. So if you want to do, say, or these density operators will also get a spin operators in it. So it will be like density operator plus T over U times some spin operator or something like that. And then using this, the density operators will depend on actually what are the spin configurations. So this is very powerful method. And just look at the Harris-Lange or canonical transformation effective models. Yes. Good. Thank you for this question. And maybe there was some other, but okay. Right. So what did we do the last lecture? Perhaps you still remember that there was this picture, that there was the d orbitals of the oxygen, of the copper. There was the oxygen p orbital, and there was another copper orbital. And what we discussed is that there is a fourth order process, the so-called super exchange, which will give us the exchange interaction between the spins on the copper sides. Another question was, is this important? Why is this so important? So the thing is that usually, very often, the Mott insulators are in a ionic solid. So typically we have some transition metal like copper, iron, nickel, whatever, and oxygen or sulfur or some other material. So these are typical very ionic solids. So for example, in the lanthanum 2 copper O4, I hope this is Harald. Is this 214? Yeah, thank you. Sorry for disturbing. Yeah. Right. So in this material, the oxygen is 2-, so it will fill its shell. It is inert, and it will take the electrons from the copper, and that's why the typical average occupancy of the copper is 1 whole. To be more precise, 1 whole spin. Also, okay, fine. Now we derived that there is a exchange where the effective Hamiltonian is J times S dot S, and maybe I write here SE, where the super exchange is positive. Positive means that if it was negative, we would like to maximize the spin and that is leading to ferromagnetism, that all the spins are pointing in the same direction, but if it is negative, it does not. There are other possibilities, so there are many chains. And for example, there will be a chain where the oxygen and the copper is in a different geometry. For example, it will be something like this. This is the copper d orbital. If you want, I can write it dx squared minus y squared. Then here is the oxygen. Say this is the px orbital. Then there is another orbital. This would be the py orbital. And here is another copper ion. What happens in this case? Let's try to figure this out. So what we do is that there is an electron here, and we can try to draw the same type of, that has been deleted, the same type of effective interactions. So we start from a case when we have two copper levels and the oxygen level. There are now two oxygen levels. There is the px and py. And there is some spin configuration here. Say this is the px. You can't see it, is that right? I shall write it bigger so that you can see it. To say px, they are same energy, but py, and there is these are the copper, and this is also the copper. This copper is connected to px orbital. It can't hop to the py orbital because if you look, there is a reflection mirror plane here, and they have different symmetries. This symmetry is such that it is even under reflection, and the py orbital is odd. So there's no hopping matrix element between this d orbital and the py orbital. It can only hop to the px. So there is only a single hopping here. Similarly, from the other copper ion, we can only reach the py orbital. So these are the only hoppings that are allowed. In other words, the situation that we had over there about the super exchange, that very complicated graph, and I've only drawn half of it, becomes much simpler. What happens in this case? The main difference is that, for example, if an electron starts its journey from copper to oxygen, it can't propagate further. It will go back. So let's try to look at it. So there is one upspin, and let's put here downspin. So the first intermediate state is that we have moved this guy to one of the oxygen levels. For example, here. And then we move so that the two spins see each other. We move the copper spin electron from the second copper to the oxygen orbital. And then what we will have the following situation, that there will be two empty copper orbitals. And there will be two spins on the oxygen sides, but on two different orbitals, right? What is the energy of this guy here? My plan A was to derive the so-called direct exchange, which I will not do because I don't have time for that. You will take my word for it, or I just refer to the Hund's rule. It says that if we have two electrons on two orbitals that are different, we would like to have a maximal spin state. So there will be an energy difference between the states where these two spins make a spin 0 or spin 1 triplet configuration. So if the two electrons are forming a triplet, this is what we want. This will have energy J Hund, while if they make a singlet, they can make a singlet, they will not contribute and they will be in a higher energy state. So this is very different from what we had in the case of the Hubbard model. So if we have two orbitals that are orthogonal to each other, the electrostatic energy, the Coulomb energy, would like them to be in a maximal spin state. The maximal spin state is a symmetric wave function. Maximal spin state is up. The full electronic wave function is antisymmetric. Electrons are fermions. So if the spin part is symmetric, the orbital part needs to be antisymmetric. And it means that we are not going to occupy those orbitals. We are not going to occupy the same orbitals, but we are going to occupy the different orbitals. And it will give us a possibility to lower the Coulomb energy, the electrostatic energy, because then the wave function is more spread. So the statistics, the Pauli statistics, and the Coulomb energy in case of two orbitals that are orthogonal to each other will lead to the ferromagnetic exchange, the so-called, and these are the Hund's rule. Hund's rules, one of the Hund's rule, which says that we want to maximize the spin here. So if we look at this process here, then it will turn out that the energy is the following. I mean, so we can have, if they were in the singlet state, right? So I will write down something and then I will try to explain, okay? So I need to draw here the final steps that you can imagine what is going on here. Down is here, and up was up there, and then we will have the final step when they exchange. This is down, this is up. Okay, so and I just, so this is one configuration so that you can separate the configurations. Right. So the energy is proportional to dPd to the fourth power divided by the charge transfer depth to the square. This is because this is this process that we have one electron from copper to the oxygen side, and also there. So this is coming from that. And we have here 1 plus 2 delta plus V plus J Hund over 2 if spin is equal to 0, and T4 PD over delta square charge transfer. And here, actually I don't need this, 1 over 2 delta plus V minus J Hund over 2. This is if spin is equal to 1. The total spin is 0 and 1. So this is if they are ferromagnetically aligned, they make a triplet. This is a singlet. And what I have written here is the energy of this state here. So 2 delta, because we have both p orbitals occupied, that's 2 delta. We have a v. The v is not the u. The v is the Coulomb repulsion between the electrons on the px and py orbitals. So if px and py orbitals are occupied, then there is a different Coulomb repulsion than between the if we have 2 electrons on the same orbital, and this is called v. Or you can say like UAB, or there are different notions. And the difference is in this part here. This is the Hund's rule. This says that if the GH is positive, so if the 2 spins are in a triplet state, it will have a lower energy than if they are in a singlet state. So the effective interaction is then the difference of these 2 guys, because this is a singlet, this is a triplet, and the exchange energy is just the energy difference between the singlet and triplet. So we can write that the J effective in this case is proportional to minus okay, there are some numbers. Okay, I don't write numbers. TPD to the fourth power divided by this transfer gap, 1, 2 delta plus V minus J Hund over 2 minus 1 over 2 delta plus V plus J Hund over 2. Fine. And this is minus 3 to the 4 power divided by delta square charge transfer J Hund over 2 delta plus V square. Right. So this, I mean, I expand, J Hund is typically the smallest, the V and delta are larger, so we can expand. So this will be an effective ferromagnetic exchange. So if we have a material, and we have many of them, I will show you in a couple of minutes. In that case, or maybe in half an hour, there will be, okay, so typically what we may have is that there is a copper side, there's an oxygen side, another oxygen side, another copper side. And it continues. And say this is kind of a chain. There are such chains. And depending on how close the copper side and the oxygens are, this angle can vary. It can be 90 degrees, but it can be bigger or smaller than 90 degrees. So if it is different from 90 degrees, then what happens is that if it is precisely 90 degrees, then there will be no possibility from, I mean, the electron will hop from here to this oxygen side, it cannot hop further. But if the degree is not 90 degrees, but some larger amount, in that case, then it will be possible for, just think about it that this is maybe, I draw with red. So this is here the, I mean, you see this is slightly larger than 90 degrees. In that case, we hop here, and there is no, this mirror X is lost. So there is a possibility to have that this electron hops further to the copper side here and back. So we have a combination of super exchange and this 90-degree ferro exchange. So depending what is the angle, one can very finely tune the J's from antiferromagnet to ferromagnet. Right, good. Okay, this was the 90-degree exchange. Any question about this? Okay, good. Fine. The title of the workshop is Itinerant and Insulating Mott Insulators. So I would like, there will be some talks that will also present what happens in lattices in systems where you have localized spins and itinerant spins. And that is the so-called double exchange. And I will show you one example for that. And that the most important material is the manganese oxides. Before going to manganese oxides, there was a question if all the d orbitals are degenerate or not. Somebody, maybe you asked it? No, somebody else, somebody asked, yeah, you asked it, yes, right. Okay, so they are not. And let's look at that at this moment. Okay, so the message here was that in the intermediate state, in the case of antiferromagnetism, the double occupied side that was favored was in a singlet state, but here in the 90-degree, it was in a triplet state, okay? Just before you forget it fully. Right, yes, okay, so d orbitals. So typically, I mean, let's look at the example of the lanthanum 1 minus x, strontium x, mangan O3. right? The lanthanum and strontium have a different valence, so changing the X composition, you can dope the material. So in one case, it will be maybe insulator of one type. If the X is, say, 1, it will be something else, and in between, we will have itinerant delocalized electrons. So what happens in this manganese oxide? Manganese, in this case, is sitting in the middle of an octahedron of oxygens. Here are the oxygens, here, and oxygen here. This is behind, and I'm just closing the octahedron. So can everybody see that this is an octahedron? Okay, so this is inside, manganese is in the center of octahedron. This oxygen, there are 2 minus, these are ions. So they are negatively charged. Now the manganese, the important manganese orbitals that play in that are important in this case are the 3d orbitals of mangan, and we have 5 of them. If this pure manganese atom would be in space and it wouldn't talk to anybody, so this lonely manganese would have 5-fold degenerate d orbitals because it would be in perfectly isotropic space. But here it is not. It is surrounded by these oxygens, and it feels the electrostatic energy of these oxygens here. And not only the electrostatic energy, but also the overlap, the T overlaps are different. So, and it is very convenient to use the following basis: dxy, dxz, dyz, dx square minus y square, and d3z square minus r square. So these are the 5 d orbitals, which are, if we write it like that, these are all real wave functions, real in the sense that they are not complex. They are real, and you can kind of represent them that here I draw the x, y, and z axis, and this xy is something that is maybe it is so there is a positive cloud wave function here, and there is a negative wave function. Let's use it. So the red will be the orbital. So there is a positive here, and the negative part along this here, something like this. So do you think you can see this? Yeah. Everything is okay. So yes, very good. Let's do it in the xy plane. So in the xy plane, yes, in the xy plane, this is it. Of course, there is a R-dependent part, and I am simplifying a lot. But essentially, this is the main idea, that in the xy plane, if this x times y is positive in this region, x times y is positive here. If we take a number from here and here and multiply, this will be positive. It will have a nodal line for y equals 0 and x equals 0. So this is becoming 0 if x or y are 0. And it is negative for y positive, x negative, or y negative, x positive. So this is something that has a positive, negative, negative, positive. So this is the shape of the d orbital. Those 3 orbitals here, they are such that they will have this symmetry on the three different planes, XY plane and XZ plane and YZ plane, okay? And you can think that they are kind of behaving similarly if we put them into this cage of oxygen, because what happens is that this octahedron has the cubic symmetry, and it transforms. I mean, the cubic symmetry. It means that it is like so-called OH, and there are 48 group elements. So it is very high symmetry. And if we say rotate the whole thing by 90 degrees, we get the same thing. And if we rotate these guys by 90 degrees, they will change, for example, one plane from the other to the other plane and so on. And they will have all the same energy. So these orbitals, they are equivalent under the OH symmetry. So you see what I mean is that this is, I mean, if you think I will try to draw the octahedron on this picture here, that there will be an oxygen around here and above and below. And then if we rotate the whole thing, the oxygen will be on the same place. I mean, they will be the same position, but the orbitals will turn from the plane of the blackboard orthogonal to it, and it will be the same energy. You can imagine that. Is it fine? Oh. Okay. So these three orbitals, they are so-called T2G orbitals. They are called T2G orbitals. They form a three-dimensional irreducible representation of these manganese d orbitals in the crystal field of the surrounding oxygen ions. So this is the crystal field split orbitals. Right. X squared minus y squared. Okay, so this was the dxy. This is the dxy. And you can guess what the dx squared minus y squared will be. We need to have positive, and this thing is positive, so it will be something like this, and something like this, and this will be positive here, and this is negative. This is the x squared minus y squared, and z squared minus r squared is such that it will be like a donut in this plane, and there will be some globe that is outside for positive and negative z. This is a two-dimensional manifold, two-dimensional irreducible representation, and these are called the so-called EG orbitals. Right. If we reduce further the symmetry, there will be further splittings here. When you ask about the copper, there was the plot, I mean, I draw the lattice of the copper, lanthanum copper oxide. It was something like this: copper, oxygen, copper, oxygen, copper, oxygen, oxygen, oxygen. So here you can see the four oxygens around the copper, and there are two other oxygens around the copper. One is above and one is below, but they are not the symmetry equivalent of those four oxygens. So this octahedron is kind of squished or elongated or whatever. In that case, these levels would further split, and the important orbital is one of the EG orbitals that is important for the copper, lanthanum copper oxide planes here. Okay, so we have these guys here. Now let's see what happens in the case of the manganite. Free z square. Yes, yes, okay. So, yes, no, if we, okay, so this is very good. So 3z squared, r squared is minus x squared minus y squared minus z squared. So it is something like 2z squared minus x squared minus y squared. So you see that it's positive if z is, if we are going in the z direction, up or down. And it's negative if it is in the xy plane. And you see that there is a rotational symmetry. This is like a R. So if you would like to draw this guy, it would be like, maybe I will try to do it. So this is like Z, X, and Y. So it is positive for Z. So we will have something that is like here. This is like two globes, and there's a ring around it. That's where it is negative. I don't know how much you can see it. So there are like two globes, positive, and there is a ring around it that is negative. That is this Vz squared minus r squared orbital. Is it okay? Yes, good, yes. Okay, perfect. Right. So manganese. The electronic structure of manganese in this material there is such that there are the T2G levels and there are the EG levels. So I'm talking about the manganese atom in octahedral environment. And I should say that this is manganese whatever plus, but I forgot. There are the two EG levels. And depending on the doping, either we have a situation when the T2G orbitals are filled, and there is one additional electron on the EG orbitals, or a situation where only the T2G orbitals are filled. I have drawn these pins pointing in the same direction. This is because of the Hund's rule. We discussed the Hund's rule for the case of the oxygen, and it also is valid here that they would like to maximize the spin component, so they will make S equal 3½ moments if the 3 electrons are on these T2G orbitals. This guy is also related by Hund's rule to the other guys, but Hund's rule these three electrons are really making a very nice, almost isotropic 3½ spin. It is this shell is kind of filled. So if we can think about this as a localized spin of speed 3½, and then there are these electrons which are either present or not, and there is another EG orbital, and they can hop around. Okay, so what is the effective model for this system? Yes. Right.
This is reverse order of orbit Energie diagram.
I have it like this in my. I don't know. Maybe it's possible.
What I mean to say is, you might just interested students. T2G orbitals have lesser repulsion. They experience lesser repulsion from the oxygens which are sitting along the XYZ direction. Their energies are lower. And the EG orbitals experience more repulsion. Their energies are that is the correct picture in manganese case. I mean, in the case of that depends on if it's elongated or sorry? That depends if the operator is elongated or no, that's right. What I'm saying is only that
Right. Okay. Yes. Sorry. Okay. So this is not an energy axis. yes. Right, yes, yes. So,
And what you have drawn is if it were energy axis and if it were tetrahedral field, then it would be okay.
yes. Okay, so there's a reason why I draw it this way, because usually this is a kind of a contour lattice model. In the contour lattice, okay, yes, Yogesh is right. I should have, if I think about this, usually all these plots were such that here was a low energy, high energy. Thank you. Yes, you're right. Yes, yes. Yeah, right. So, yes. Yeah, okay, right, yes. Here are the conducting electrons. And the Hamiltonian is as follows. Minus T times C dagger C I sigma J sigma plus Hermitian conjugate minus J Hund times alpha beta C dagger alpha side I S dot sigma alpha beta underscore C beta I plus U times sum Ni up, Ni down. Yes, what is this? Here, this describes the hopping of the Eg electrons. Right. This describes the Coulomb repulsion of the Eg orbitals. This part here describes the Hund's rule between the T2G s equal 3/2 spins that we treat as localized times the spin of the itinerant electrons, which is nothing else but this C dagger alpha times sigma alpha beta Pauli matrix times C beta. The alpha index is going over the up-down spin, and the beta is also going up-down spin of the spins of the Eg orbitals. And when we combine this C dagger alpha, sigma alpha beta, C beta, that will give us the S matrix. So S mu, this is the spin of the spin 1/2, is equal to C dagger alpha sigma mu alpha beta C beta sum over alpha beta. So we take the spin up down of the electrons, we take the Pauli matrices, the X, Y, Z Pauli matrix, and we make this multiplication, and we have the C beta from here that will multiply the lower index of the Pauli matrix, and mu Pauli matrix is telling us the spin mu component of these 1/2 spins. Let's see an example, because you don't seem happy.
Karlo, I
Yes.
have a question. So the reason you have not written the bare exchange terms within the T2G manifold is that they're usually negligible.
They're not.
Huh?
They're not.
They're not. But they also have a component where you integrate out the EG.
And these are very important. Thank you.
Okay. Thanks.
Yeah. Yes. Thank you. So clear. So let's see how does this work. So the SZ of the itinerant electrons is equal to, we look at the sigma Z, the Pauli matrix sigma Z is just 1 minus 1. Maybe there is 1/2 here. Let's write here 1. It depends how you define your sigma. So this is it. So it will be 1/2 times. We have only the, and here, this is the up sigma z matrix element. This is the sigma z down. Is it fine that what I write here? Okay, everybody? This means no, yes. Not very happy. Okay, so right, so you have like the problem with the big linear board is that the sponge is far away. So he will have the up component, he will have the up down. That's right. Down, and down, up, something like this. So these are the different parts in the sigma. Yeah. Right. So if the sigma z has only up, and down, so it means that if we look at the sigma z, so there will be only up, and that will be positive. So it will be just C dagger up, C up, minus C dagger down, C down. And that is equal to 1/2 and up minus and down. Very good. This is something that is already more familiar. I mean, the SZ component is just the difference of the occupation of up spin minus the down spin. Good. If we look at the SX or S plus, it will be just like, for example, S plus will be just C dagger up, C down. This would be the S plus operator where sigma plus is just like 0, 1, 0, 0. Now I don't know where is the 1 here or here, but something like that, okay? So this is what is standing here. So this is the model that people look at when they want to describe the manganese oxide or other materials where we have localized spins and itinerant spins. So, and this is called a condor lattice. Loosely speaking, the real condor lattice is with negative, with antiferromagnetic exchange. And this is the interaction between this is the hopping part of the itinerant electrons. This is the coupling between itinerant and localized electrons. And there is also exchange interaction between the localized spins. Okay? How do you feel about this? Right. What does this know? What is it able to tell us? So, okay, so let's concentrate on the two cases. Maybe here. This is the free half spin. Again, a free half spin. There is one electron that is on the EG orbital that is parallel to the spin free half spin. And another spin free half spin is parallel to this guy. So this spin can freely hop because the energy before and after the hop are equal. On the other hand, if we have a situation where we have the large spin pointing in the opposite direction, then this guy that is parallel to the free half spin, if it would hop, it can, during the hopping, we don't turn the direction of the spin. It will be in the antiferromagnetic direct, I mean, it will be opposite to the large local spin. So it will lose Kunz energy. It will lose a lot of energy. So if it wants to hop, it's difficult to hop because it needs to invest energy. So it means that if all the spins are parallel, then the electrons can freely move in the system. If it is an antiferromagnet, then they become localized. They cannot hop. And in this case, the resistivity is much lower, much higher. Okay. And we can also turn a little bit the picture different. We can say somehow differently that if there is a sufficient number of itinerant electrons, they are, and this J is not sufficiently large, in that case, the itineracy of the electrons will make the local spins ferromagnetically aligned. So this is itinerant electrons driven ferromagnet here. And in this case, it is not going to happen. This double exchange is something that is used in the hard drives. So this is the mechanism. I mean, if you make your head of your hard disk from a material that is like this, in that case, depending on the magnetic field of the plate below, I know today we have SSDs, but earlier the resistivity would very drastically depend on the magnetic field, because the magnetic field will interact with these localized spins and try to make them more ferromagnetic, and it will decrease the resistivity, to decrease the conductivity. And these guys are called, they have a so-called colossal magnetoresistance. So if they check the resistivity against magnetic field, their response is huge, much larger than, because there was a gigantic magnetoresistance that was for multi-layers of different metals, but this was even larger. So this has been studied like 20 years ago. Yes, please.
Do we know of systems where the J physics and the Hund's physics compete?
Even in this material, they compete, because you will have antiferromagnetic phases and ferromagnetic phases, depending on the how large is the doping.
I see.
Yes.
I see.
So essentially, when there is no doping, then it will be more antiferromagnetic. If you introduce doping, there will be. So the phase diagram is very rich of this material. Yes. How do I stand with time? Badly.
So I think we have like
Half an hour. Right. Okay. Good. Fine. So far, okay, so there were these T2G orbitals, and okay, everything that I was telling you until now were isotropic magnets. So the spins didn't, I mean, we have S dot S here, and so on. So they were all isotropic. The spins didn't know about the lattice. But there will be cases when they will know about lattice, and that is when the spin-orbit coupling plays a role. So before you asked me, I think, for example, if you put this term into pyroclass, in that case, you will get all, probably Motomer-san will give a talk. The reason I'm mentioning this is that there will be a talk by Motomer-san about itinerant such systems in frustrated environment, and then it gives rise to very, very, very interesting phase diagrams and phases of matter, right? Okay, so spin-orbit coupling. Spin-orbit coupling is a relativistic effect. What happens is that, okay, so yeah, first let me delete it, and then this is plan D, or E, or whatever. Good. I also wanted to show you some slides, a few slides. I'm hesitating what to do. Do you think we can lower the screen, please? Right. While it's getting lower, I will try to explain the origin of the spin-orbit coupling. Suppose that you have an atom, and there is an electron orbiting around it. Z, there is an electric field that is keeping the electrons in the orbit. Now, if the electron is traveling in this electric field, and we sit on the electron as it goes, it will experience an effective magnetic field in its own local frame of inertia. What? In its local frame. So, if an electron or charge, a moving object with velocity v is propagating, is going in the electric field with some velocity v, then there will be, it will experience a magnetic field that is proportional to E cross V. Okay, so this electron will feel a B that is proportional to V cross E, something like that, and this B will interact with the spin 1/2 of the electron. So, and this interaction will lead to the so-called L dot S term in the Hamiltonian. This will couple the orbital momentum of the electron. L comes from for the d orbitals. It can be L equal 2, so it will have L equal to moment that is interacting with the spin 1/2 moment of the spin of the electron. Or for the p orbitals, this would be 1, the L is 1, and this will be 1/2. For f electrons, this L is 3, and the S is equal to 1/2. And this term is larger. The heavier the nuclei is, it goes to the Z to the maybe 3rd power, and it becomes important for the 4D and 5D and essentially 4F electrons. We were talking until now, usually manganese is 3D or copper is 3D. In that case, this is not so important. But for heavier elements, this is important, and it will connect the spin and the orbital moments. But now, since I have the screen, I would like to share it, and I think I need to share my screen. And okay. Aha, you see something. Let's see, I have a few keynotes here. Okay, so this first keynote, I forgot what, maybe I need to play. Let's see if it works. Do you? It's always a trouble. I hate this. Really hate this. You see that I didn't give too many Zoom talks. I don't know what to do. I'm sorry. I hate this. I really hate this. Can you help, please? No Hebrew, please. So until that, this is getting fixed. I may maybe stop sharing and start. We tried in the break. It worked in the break. He made it work. But maybe we leave it like this. I see something. This is okay. Right. Okay, so this was just a paper from, yeah, thank you. Just pointer. Yeah, right there. Okay, so this is the lanthanum copper oxide. This is the parent material antiferromagnet. You see the copper oxygen plane. And these are the oxygens above below. You can see that this is the blue is the copper, and it is, you don't really see it very nicely. Yeah? So there is this oxygen, copper here, and there are the 4 oxygens around it, above and below. And this is the octahedron, and these are the possible passes. And people did neutron scattering measurements. It measures the dispersion of the excitations of the underlying spin 1/2 antiferromagnet, and to be able to describe precisely the modes. What you see here is that this should be flat. In the very naive calculation, when we have only nearest neighbor exchange, this mode should be flat, but it is not flat. And then Radu Kolder and other people, they invoked the Forsyth ring exchange to explain this behavior in the spectrum. So you really need to do some elaborate experiments to see this. What else is here? Okay, I think I will skip this. And let's go to the next here. This is about the colossal magnetism. I mean, this, well, this is what or shall I not? I just place this here. Okay, very good. Now, this is the phase diagram of the manganites. And what you see here, this is the X. This is lanthanum strontium mangan oxide. This is the energy level scheme. Yogesh, you were absolutely right. This is the as correcting with the energy. And there is additional further splittings here. But essentially, there are the S3 halves and the itinerant electron here. And this is the phase diagram. So if X is 0. Around 1/2, then in that case, the itinerant electrons are missing. And in that case, we have an antiferromagnet made out of the 3/2 spins. If we decrease it, it becomes ferromagnetic. And then there will be other phases like charge commensurate. Sorry, I forgot what are the Ci and Fi's. So very complicated phase diagram, and you can replace the lanthanum with neodymium or praseodymium and strontium with calcium and so on, and then you have different phases here. This is the resistivity against magnetization, and this is, you see if the magnetization is growing, it means that the spins are pointing more and more parallel, the resistivity is dropping. So the more parallel the spins are, the smaller the resistivity, the larger conductivity is. Okay, good. Okay, this is different. And then the 90 degree, where is the 90 degree? I hope I didn't close it. Super, yeah, this is it, perfect. Yes, so this is super exchanging cuprates. So this is the susceptibility as a function of temperature. And from this, they extract that the exchange, effective exchange in this strontium copper oxide, this is the material itself. You see that it is made out of chain, copper, this is the copper here, and the oxygen is the black disk. So we have kind of chains of copper ions, and they are separated by the strontium ions in between. So this is a 1D chain, and in this case, the effective J is 2000 Kelvin. This is another example. This is strontium copper O2, and here what happens is that it is like a zigzag chain, and then it is like it depends how you look at it, either 2 decoupled chains or weakly coupled chains. Now, what you see here, this is the copper lithium to copper O2. This was interesting in the late 90s. Here, the copper is, I mean, the oxygens are these empty disks. These are the copper is the black disk. And you see that we have these almost 90-degree bonds here. So what happens is that there is a very weak ferro or antiferro interaction between the first neighbors and a second neighbor interaction that is roughly of the same size. So we have a competition between the nearest neighbor and next nearest neighbor coupling in linear chains. Here, this is an experimental plot of the effective J1. In materials, there are different chain materials, and the theta angle between the copper-oxygen-copper path varied from 80 to 100 degrees, and you see that there is this region where it is ferromagnetic around 90 degrees, and then it really very sensitively depends on the degree. Right, so this is about the 90-degree exchange here. Yes. And I think this was all for the moment. Thank you. I think this was all. Thank you. Good. I think we can perhaps raise the screen. Right, good. So we need to understand. There was one more. Is it still alive? Is it still alive? Let's see, one moment. I had one more. I had one more. Where is it? The DM interaction. Yes, this one. I need to share my screen. Oh, yeah, launch meeting. Hello, sorry. Come on. Share screen. And I need only one slide. And yes, this here, this one, only this. The first one. Yes, this is it. Right, okay, so this is a Jaroszynski-Moriya interaction is coming from the spin orbit coupling. So what you see here, this is the material iron 2O3. It is essentially iron atoms that have large moments, 5½ and yet it showed a weak antiferromagnetism, and people didn't know why is it there. And then Jaroszynski looked at the symmetry of this magnet, and he considered what are the symmetry allowed terms in the Hamiltonian that can be present. And when he looked at these terms, he found out that there is a term of this form that is by symmetry. This is a lower symmetry compound. It is distorted. You see that it is very stretched. And he added this term here, which what it did this term is to count the spins. And so we have essentially an antiferromagnet with little bit canted spins. I will, if I have time, I will derive this Hamiltonian. And in that case, there was a weak antiferromagnetism. And this this term, Jaroszynski, it's called Jaroszynski-Moriya interaction. Jaroszynski derived it using symmetry arguments, but Moriya, in next year, he derived it using microscopics. Microscopic derivation involves taking into account this term here, and it is quite involved, and I will not reproduce it here. I will only present the symmetry argument. I'm finished with the presentation this time. Thank you very much, and sorry for this interruption. Right. So let's try to figure out how does this work using symmetry arguments. The name of that crystal iron oxide is hematite. Right, so suppose that we have a bond where we have a copper, another copper, and then oxygen that is off the center. So we had the superexchange when the oxygen was precisely in the center, but it may happen for different reasons that it's not in the center, but it's slightly off. What happens in this case? What are the possible Hamiltonians that we can have? So what is the symmetry of this problem? what we have, there is a winged axis. So the axis is as follows. This is the x, so the bond is around the x direction. The oxygen is out of from the center in the y direction. And we have the z direction coming out of the plane of the blackboard. The symmetry is we have a C2y. This is side 1, this is side 2. So this C2y is rotating our system around this axis. So the copper will go to copper 2 and copper 2 will come to copper 1. This is fine with you. What other symmetry do we have? We have a mirror plane. The blackboard itself is a mirror plane because if we apply the mirror to this picture here, the oxygen stays where it was and the copper stays where it was. So let's see what happens if we apply the C2y and the sigma. I will denote the sigma with sigma xy. So the x and y are not affected by the plane. So how much time do I have? Okay, good. C2y sigma y, and let's see what happens if we apply to x, y, z, and Lx, Ly, Lz, or Sx, it could be a spin component, it doesn't matter, and side 1 and 2. So the C2y, it makes a twofold rotation around the axis that is in the plane. So it will change y 1 to 2. So one side becomes 2 and side 2 becomes 1 under this rotation. Okay. The y axis is not affected by rotation. The x axis, if we were pointing something in this direction, it will be pointing in the opposite one. So this is minus x. And similarly for the z, it will be minus z. Now, how do I transform the spin operators, the momenta? Momenta are not vectors. X, y, z, these were components of a vector. The magnetic moment is not a vector, it's an axial vector. You can think about it as some rotating electron. Rotating, and let's try to do the mirror compared to this plane of the desk here. So it is rotating in this way, and the mirror image is rotating in the same way. So the component that is orthogonal to the plane does not change. The component that is orthogonal to the plane does not change, and that is the z component. So here I shall write L. Is that right, what I'm saying? It's right. Okay, yes, it's right. Good. If this is the mirror symmetry, if I have something that is rotating this way, I will try to do it. It's not so simple. You have something like this. It means that in one case it's pointing to the left, in the other case it's pointing to the right. You see this? You can try to, yeah. Right, so the Lx and Ly component will change. I'm sorry, I scoot it up, it goes here. My apologies, I was talking about the mirror plane here. Mirror plane here, it comes here. Right, so the LZ was fine. The Lx and Ly got minus sign. Yes, like this. I need to be careful because time is running. This is right. You think? Okay, good. Right. Here, what we have is that sigma xy this remains, this changes sign. Okay, good. And the C2Y is just rotating things. So if I'm rotating this way, it will follow. So it will, I mean, under rotations, the pseudo vectors, axial vectors, and the vectors, they transform the same way. So it will be minus Lx, Ly, and minus Lz. So these are the symmetry, the transformation of the vectors and axial vector under the rotation around y-axis and the xy plane. Yes, perfect. Thank you very much. Right. Very good. Now, what is the possible Hamiltonian that we can write? So the H, we can write H as a J alpha beta S alpha S beta. The Hamiltonian needs to be invariant under the symmetries of the problem. Now including special symmetries because we have a connection between the spin and the orbitals. Let's see what happens to the, can we have XY orbital, XY XZ interaction? So we have like, I should have written SZ, but anyway, so this, yeah, good. So this can be L or it can be S. L or S, they are the same. I don't want to make a mistake because time is running out and I have written here the next S. So if we have S1, S2, Z, and we apply the sigma XY, this guy here, then what it will do is that it will not affect the order of the spins. It remain the same. So it will be JXZ, S1, S2, X will get a minus sign, and the Z will get the, thank you. X will get a minus sign, and Z will not get a minus sign. So this will go to minus S1X, S2Z. So clearly, we have changed the sign of this term in the Hamiltonian, and because of that, this can't be in the Hamiltonian. Let's look at another one. Let's look at the JXY, S1X, S2Y. And again, we look at the sigma XY. What it does is that XX and SY are both changing sign. So this is allowed term. Right? Minus SX minus S2Y, which is equal to JXY, S1X, S2Y. Very good. This is allowed. We can go through and check what is allowed under sigma XY, and it turns out that the Hamiltonian that is allowed, and here I'm only writing the off-diagonal parts, I'm not talking about the JXX, it will be the JXY, SX1, SY2 plus JYX, S1Y, S2X. Okay? These are the two terms that are allowed by sigma. Now, let's apply also the C2Y symmetry element. So what it does is that if we apply the C2Y to the JXY, SX1, S2Y, what it does is, I just write this here, it will exchange the side indices. 2 becomes 1 and 1 becomes 2. The x will become x and y. Let's see, x and y, x and y. One of them is changing sign. So this will be minus here. And this is x, this is y. Is this correct? Right? And we can rewrite this as minus jxy s1y s2x, which is the same, and the corresponding term in the Hamiltonian, and this needs to be equal to jyx s1y s2x. So from here, we got the condition that these two coefficients in the Hamiltonian needs to be equal. So it means that if we also include the c to y, in that case, the Hamiltonian becomes jxy s1x s2y minus s1y s2x. And this is nothing else but the so-called S1 cos S2 times D, where the D vector is pointing like 0, 0, Z. This is the D vector. So this is how we can derive, and how Jaroszynski in 50-something, 8 maybe, derived the effective possible allowed symmetry allowed Hamiltonian for the hematite, for the iron 2 oxygen 3. Is there any question regarding this? Wait, microphone is coming.
Why we did not change minus jxy to jyx in that case when we were doing for the mirror plane?
What? So here?
Yeah.
What I mean here, I'm not sure if I understand your question correctly. You mean that there is some problem?
Yeah. So there we said that that is not a possible case. Like,
yes, that we can't have it because it changed its sign. No, this one here. Yes, we can't have it because we have. I mean, we have the same sides, and if we apply the xy term, what happened is that it changed the sign of the xy. It changed the sign of the x component. So this became negative, and that is the sign here. So we have this term in the Hamiltonian. We apply the symmetry, and we get the negative of that term.
yes. So, like in that case also, what is the?
The difference is that here we had a different. I mean, we are trying to we applied this term to the Hamiltonian. I mean, this is the term in the Hamiltonian. We applied the symmetry. We arrived to this one, but this is not the same because we have the different indices. So this can be recast into this form, but this form already exists in the Hamiltonian, but with a different coefficient. So if we want to allow this term to exist, we need to allow for the jyx term to be negative of this.
Okay.
Because then it will survive this symmetry operation. Does it?
Yes.
Right. Okay, so how much time? 0? Minus epsilon. Okay, so let's stretch this epsilon a little bit. Just a few remarks. So what you saw here is that if we have this oxygen, not in the center of the bond, but slightly off, Then there is a term that appears, which is proportional to the S1 cos S2. This term, this is a triple product. It wants to span a volume with D, S1, S2. They want to have a large, I mean, they don't want to be in a plane. They want to span a volume if possible. So if we have a configuration when, I mean, this typically arises next to an antiferromagnetic exchange. Antiferromagnetic exchange wants to make the spin antiparallel. And this term would like to have some finite volume. So suppose that the D vector is pointing out. So what it will do, it can gain volume if the spins start to tilt a little bit. And if they tilt, then the DM interaction, they will reach some compromise between the DM and the Heisenberg exchange, and this type of magnetism will arise. It can give a small ferro component or whatever. Another point is that the oxygen was not in the center, but slightly off. This is charged 2 negative. So this corresponds to something that we have kind of a polarization in this direction, electric field in this direction. So if we would apply electric field, we would induce this time of term in the Hamiltonian. We can think also differently. So suppose that we have some spin configuration where the spins are not parallel to each other, but which have some angle. If this is so, it is possible, and this really happens, that the non-collinear spins will give rise to electric dipole moment. And this is the so-called magnetoelectric coupling. And it is made possible because of spin-orbit interaction. Magnetoelectric coupling, I mean, this is the Katsura-Balatsky-Nagosa mechanism, I think. It had been shown in this, like you have this J1, J2 spin chains where you have different first and second neighbor. Then you will have like a spirally state. It will stabilize the kind of a state that is spiral, where this angle is finite, and then it will give rise to the finite ferroelectric moment in those materials. And these are the so-called multiferroics. When you have coupling of the spin and of different fields, like magnetic field, spins, and electric fields. Since epsilon is small, I'm over the epsilon. I thank you very much for your attention. There are some things that I couldn't tell you, many interesting things, but anyway, I've chosen to go slowly and not to overload you with different things. Thank you very much.
Thanks, Karlo. Would you briefly comment on single ion anisotropies?
We can, why not? Yes, so spin orbit coupling is, okay, so one of the reasons, spin, okay, so spin orbit coupling can lead to DM interactions, but even more importantly, if you have a higher spin, like spin 1 or spin 3/2, then terms in the Hamiltonian can appear like S1Z square. Such terms can appear. Or if you think about some more complicated systems, like a tetrahedron that is found in the spin ice, then these spin ice these anisotropies will choose axes that are pointing from the center of the tetrahedron, and this will be special axes. So it can either give rise to the so-called Ising-like anisotropies, when the interactions are not anymore isotropic, but more like Z component is interacting with the Z component, and we forget about the XY, or maybe more like the X and Y components is more quantum-like. In that case, we can kind of differentiate between the two regimes, Ising, isotropic, Planck-like behavior, and this gives also some more interesting physics in these materials.
Any questions, comments, or thoughts you would like to share? If not now, since we are pretty localized in ICTS as a
Yes.
Mott insulator, and given the heavy rains, there's a large charge gap to go to the city. You're free to catch Karlo on any of the blackboards outside
Yeah.
and discuss more, or if you want to discuss more advanced things from here or better understand. Karlo is around for the next 2 weeks.
Mm.
Are there any questions or comments from the online participants? Okay, doesn't seem to be the case. So in which case, let's thank Karlo again for actually giving 2 back-to-back lectures. And we'll go for lunch, and we should reconvene at 2:30. There's a talk by Ronny Thomale on Kagome metals, followed by a talk by Philippe Gegenwart on rare earth Kagome metals again. So it's an exciting metallic session in the afternoon. And so, yeah, let's head for lunch now then.